So in this video, we are going to discuss the basics of a bilinear quadrilateral element in reference to a typical rectangular element. You must remember that we are still using the thin plate theory as we have discussed during discussions about the triangular element. So we are going to only consider in-plane loading conditions, therefore it's an in-plane problem. For simplicity, I'm only going to consider a certain unknown, u, which is going to be at all the different nodes of this element. As you can see in the figure, a typical rectangular element is consisting of 4 nodes. Therefore, I will have a minimum of 4 unknowns in this problem. I can also enforce a certain condition because it's a bilinear quadrilateral element that the function, which is unknown, varies linearly along the edges. So if the function varies linearly along the edges, then there will be a certain nonlinear behavior within or inside the element space. So considering these two particular conditions to be applicable, this element is called therefore a bilinear element. The procedure for deriving any relations or any kind of stiffness matrices, etc. for such an element always, as usual, starts with defining the behavior of this element. And the behavior of these elements is going to be related to the shape functions that need to be first arrived upon by means of this linearly varying function. So for simplicity, of course, if you can consider that this is in a two-dimensional plane, so if I just draw the global coordinate axes, then I know you have x and y, but just for simplicity, for derivations and keeping it simple and clean, I'm only going to do the shape function derivation for one unknown, which is u, and not the displacement in the y direction, which is v. So let's start with the derivation of u. So if I say that I have a behavior, unknown behavior ue, which is belonging to the element, we can approximate the distribution of this behavior across the rectangular element by means of a linearly varying function, where you would have 4 unknowns, therefore 4 constants that need to be found out. So I will have a function c1 plus c2x plus c3y plus c4xy. So this is of course a linear function along the edges. Now, if I consider a local coordinate system, of course, x small y, then I will have at certain directions, if I know the distances, like if this edge is L and this edge is given as W, then I can also say that I can enforce certain conditions which can be written as u is equal to ui at x is equal to 0 and y is equal to 0. So what I'm trying to enforce here is that at this location x is equal to 0 and at this location also y is equal to 0. And as we move on in this direction, here I come upon L. The same way here I would come upon W. So u is equal to ui at x is equal to 0, y is equal to 0, and in the same way I can have u is equal to uj at x is equal to L and y is equal to 0 because y hasn't changed. U is equal to um at x is equal to L and y is equal to w in this case because we moved up along y, and finally u is equal to un at x is equal to 0 and y is equal to w also. So now if I have these following conditions, then the displacement function ue should satisfy all these different conditions. So if we apply these conditions to the equation for equation 1, let's say, so if I say this is equation 2, so if I apply 2 to equation 1 and solve, must continue writing here, and solve for unknowns C1 to C4, then we will get the relations for C1 to C4. We will get here C1 to be equal to ui, C2 will be equal to 1 by L uj minus ui, C3 will be equal to 1 by W un minus ui, and finally C4 would be equal to 1 by LW ui minus uj plus um minus un. So if you do the calculation, which is quite fairly simple, you just have to substitute 4 different criteria for u into the assumed displacement function and solve for the 4 unknowns. If you substitute, you will get back C1 to C4. Now, as usual, you know the entire process. I will continue to substitute the values of C1, substitute C1, C2, C3, and C4 into equation 1 that I defined in the beginning, and rearrange such that I arrive at something like UE is equal to something UI plus something uj plus something plus something un. And of course, this something is nothing but the shape function ni, nj, nm, nn. So if I have this distribution, then I will be able to get the shape functions, and in a more compact notation, I can also write this as ue is equal to ni, nj, nm, nn times ui, uj, un. The shape functions, of course, I would also like to write down here because they are quite important also to see what they look like. The shape functions will look like ni would be equal to 1 by x by L times 1 minus y by w. Sj, I'm using notation nj is equal to x by L times 1 minus y by w. Nm would be equal to xy by Lw, and finally Nn would be equal to y by w times 1 minus x by L. So these are the different shape functions that we will arrive at in the standard coordinate system that we are already used to. So up until this point, I want to use the standard formulation for elements, like just using x, y as the coordinate system. That means we are moving from limits 0 to L for direction x and 0 to W for direction y.